Welcome back. Today we're going to talk about Chapter 10. This is rotational motion. A lot of it looks a lot like Chapter 6. There's some similarities and some things that we will recycle here. But here's the first of them, angular velocity. We already know that the angular velocity is the speed of rotation. It's how fast the thing turns on its axis. It's the rate of change of angle. And all I have to do is use this omega. The angular velocity, it's simply the change in angle over the change in time. If you had the Earth here, my Earth is not rotating, it's supposed to, but that thing would rotate around through 360 degrees in 24 hours, and you could work out the 15 degrees per hour would be one way to do the angular velocity. You could also do that in radians, 2 pi radians every 24 hours and work that out. But we've seen angular velocity before. Nothing too surprising there. Angular velocity can change, just like we have a change in velocity and call that acceleration. If I have a change in angular velocity, that is the angular acceleration. So there's that word that we tack onto the front, and all we have to do is say how much did my angular velocity change. You could also write this alpha, the angular acceleration, is equal to the final angular velocity minus the initial angular velocity divided by the time. And if you know those two numbers, then it's really easy to work that out. We saw some of this in Chapter 6. Anytime I have a circle, then the circle goes around like this. The radius is the distance from the center to the edge. And if I imagine that radius spinning through some angle theta right here, that is to say my circle was right here and it rotated around, so now that line is over here moving through some angle theta. Those are connected. S, the arc length, is equal to R, the radius, times theta, the angle. Please remember that theta needs to be in radians for this to work out, right? So don't forget about that. We've seen that part before, the arc length formula, and that's a handy thing as long as your angle is in radians. But I also have two more here that I want to tell you about. The velocity of a point on this, if I imagine this spot right there, its velocity is moving that way, and then a little bit later it's going off, it's going to rotate around, moving around the circle like that. But that linear velocity is related to the angular velocity, the speed of rotation, and this formula tells us how to do that. The linear velocity v, the old kind of velocity, equals the radius times the angular velocity, and again that should be in radians per second for omega. Okay, one last one here that also makes sense. If the point right there is speeding up, right? I've got some acceleration vector here. You can see that means that my circle is also speeding up, and those two have to go together. This should be in radians per second squared. So those three formulas there are really handy to get back and forth between the linear variables and the rotational variables over here, theta, omega, and alpha. And so if you just kind of stow those on your index card or wherever you need to put them, we can get back and forth between distance and angle, between velocity and angular velocity, between acceleration and angular acceleration. Here, with those three in place, we can start to make some generalizations, and we can rework everything that we know about kinematics. We can recycle everything that we have so far. In Chapter 2, we had these three formulas right here, and we worked all kinds of problems. A car is moving this fast and it accelerates for a period of time. How far does it go? Those type of problems. What we're going to do here is to change everything over so that we have that for rotational kinematics, so that we can figure out if a wheel is spinning and it's speeding up for a certain amount of time, what angle does it turn through, or how fast does it go? You can see here that all we've done is replaced the variables. X became theta, V became omega, A became alpha, all the way down, and now we have a whole new physics, a whole new rotational kinematics that works for rotating objects. Over here in the corner, I've worked one of those for you, but you can see where the others come from really quickly. Remember here that those on that last slide, we said that V was equal to R omega and A was equal to R alpha. So if we simply take those substitutions, right here, we're starting with this formula, V equals V naught plus AT. V is equal to R omega. So if I pick up R omega and put it right there, and an R omega naught and put it right there, and an R alpha and put it right there, then I would end up with this expression, R omega equals R omega naught plus R alpha T. And then you can see that there's an R in every term, so those are going to cancel out, and I end up with this expression right there. The final angular velocity is equal to the initial angular velocity plus the angular acceleration times time. What that's really saying is that I can find the angular velocity at any point in time if I know how fast it started out spinning, and it's speeding up for a period of time. That's going to make it go faster, and I add that to the original angular velocity, and I get the final. So these make very good sense. They work just like the other formulas do. Right here, the distance, not the distance so much, but the angle that I rotate through is equal to the angular velocity times time plus 1/2 AT squared. Again, perfect symmetry, perfect parallel to the distance formula that we had. Here is V squared formula. We turn it into the omega squared formula. And here's the one that we worked out in the corner down here. So I hope you can see where those come from. Again, just substituting V equals R omega, A equals R alpha, S equals R theta if we needed to. And we can cook those up pretty easily. Let me actually go back here and we'll do just one or two of these problems so that you can get a feel for how those would work. Let's say that we have a some kind of disk that's turning. Here's the axis of that thing, and it's rotating like this at some angular velocity. Omega naught equals 4 radians per second. And if I know that the acceleration of this thing, the angular acceleration, is 2 radians per second squared, and it does that for a time of 8 seconds, then with those formulas that we had, omega equals omega naught plus alpha t, and so here that would be 4 radians per second plus 2 radians per second squared times 8 seconds. The seconds are going to cancel out there. 2 times 8 would be 16. 16 plus 4 would be 20 radians per second. I could also find out the angle that it would turn through in that much time. And so there is the parallel to the distance formula. And I put my numbers back in here, 4 radians per second for the angular velocity, initial angular velocity. It's going to turn at that for 8 seconds. So if it weren't speeding up, 4 times 8 would be 32, and the seconds cancel. I would have moved through 32 radians, would have rotated here. If I draw an R and let that thing rotate through some angle theta, 32 radians would have been my distance there. But I am speeding up, and that means that I'm going to cover some more distance here. And so I have to add 8 squared would be 64, and the 1/2 and the 2 cancel out. So here's 64 radians. Again, the seconds get squared, so that'll cancel second squared. I'm in radians, and this would be 96 radians that I would rotate through. So see how they work exactly like the old formulas and do the same kind of problems. things are rotating. They're moving in circles instead of straight lines. Other than that, it's exactly the same. Now, when we think about Newton's law, we had F equals ma, right? There's Newton's second law right there. So we're going to play a little trick right here. Here's that substitution, A equals R alpha, that we've used before. If I take R alpha and plug it in right there for A, then I would have F equals mR alpha. What we'd like to do now is to multiply both sides by R. So we've multiplied on the left by R and on the right by R. That R and this R would make an R squared. Remember, the force times the distance is equal to torque. And guess we haven't really done torque the way we've rearranged the chapter here. So I need to take just a moment and tell you about torque, don't I? Torque is force at a distance. So if I have an object, let's say there's a door right here, and here's the doorknob and the other doorknob, and I've got a hinge over here like this. If I apply a force to that door, then the door is going to rotate through some angle theta, like so. And specifically, when I apply a force to the door, it makes a difference where I apply that force. So, if I apply the force way out here, if there's a distance r from the hinge point, from where the door rotates about, then I have to know both of those things. I have to know F, how hard I'm pushing on the door, and R, how far away from the hinge I'm actually pushing. This would be a very different problem if I pushed over here, or even if I pushed at the hinge. Try it sometime. When you go through a door, push right up near the hinge, the door won't hardly open. You have to push very hard to make it work. We call that concept torque. And again, torque is simply the force times the distance. The lever arm, the moment arm, it has different names, but it's the distance from our point of rotation. So we've got that torque right here. Force times distance is torque. Over here on the right-hand side, I'd have m times r would be r squared times a. And that's an interesting formula. When we write torque equals m r squared alpha, you can see that since we started with F equals ma, and you know that A is related to alpha and force is related to torque, then there's this thing in the middle. Mass is the quantity that determines how much acceleration I get when I push on an object. If I'm pushing on a little matchbox car on the table, that moves pretty easy. A small force will give it a large acceleration. If I'm pushing on a refrigerator, something very massive, then I have to push a lot harder. And that mass is the quantity that has inertia, that wants to keep it in the same state without any change of motion. Well, when we get down here to this new formula, this mr squared is the companion to mass. So in the linear world, I would talk about mass. But in the rotational world, this new formula, then I need to have this idea of mass times the radius squared gives me a quantity called I, and that I is referred to as the moment of inertia. The engineers just call this moment. So you may have heard that name. But to be a little more explicit, we call it the moment of inertia. It is the quantity that tells how hard it is to get something rotating. And so it's an important quantity. Object rotating. There we go. It would also make it harder to stop it. If something were rotating and you tried to stop it, the mass would be important. The more mass it has, then the harder it is to get it moving or to stop it moving. And the larger it is, the harder it would be to get it moving. In the little picture here that I've already messed up with all my chicken scratch here, we've got a rock that's tied onto a string. This is a single point mass right here, and it's moving in this circle. So it goes around and around, and you can see that there's a force acting on it that makes it do that. That force at a distance gives me the torque that I need to cause rotation. And again, maybe that's worth writing in here. Torque causes rotation. It is the quantity that causes things to move in circles, to move, to rotate. Rotation, not sure what's happening here. So it's an important quantity, but I've got this object, it's moving around in a circle, and you can see here if I had, a little, I don't know, test tube stopper tied on right there, then that's not a whole lot of mass, so it wouldn't be very hard to get it going. If I had a concrete block tied on right there, I'd have to work a lot harder to get it to move in the circle. On the other hand, if I had a cork, a little bitty lightweight thing on a string that was 1 meter long, that wouldn't be too hard to spin. But as I let that string get longer and longer, as R increases, as this number increases, then my moment of inertia increases. It becomes harder to get it to rotate. So I have to have both of those quantities. How much mass are we talking about, and where is the mass relative to my axis of rotation right here? If I have more than one object that's rotating, if I have multiple point masses, and here in the picture you can see that I've got that axis of rotation. So maybe I've taken a dowel, a stick, and I've stuck it in a motor, and I've tied a string with a rock, and another string with a rock, and another string with a rock. And when the drill motor turns, it's going to turn that dowel, and then all of those objects are going to rotate. To get the total moment of inertia, I would have to add the individual moments of inertia. If this one is 6 and that one's 8 and this one's 2, then I would go 6 plus 8 plus 2 is 16. Okay? So that's all this is saying. The total moment of inertia is equal to the first moment of inertia plus the moment of inertia of the second object plus the moment of inertia of the third object plus ... If you had 15 objects, you just keep adding the individual moments of inertia here. Each one of those moments is equal to mr squared. So this would be the first mass times its distance from the axis of rotation squared, plus the second mass times its axis of rotation, or the distance from that, plus mass 3r3 squared, plus ... Keep going. There is a little shorthand notation we use here. This is the Greek letter sigma. It stands for summation. When we want to add things up like we're doing right here, we can write this sign and say take the m sub I, and then we're going to let I go from 1 to n. So the first time out, I is equal to 1, and we'd have m1 r1 squared. And then the next time, I would bump up to 2, so we'd have m2 r2 squared, and we'd add that to what we already had, and it would go to mass, n would, I would go to 3, so this would be m3 r3 squared. Add that to what you already had, and that way you'd get the total moment of inertia of these objects. Just adding all the individual pieces, we would get the total. So nothing too bad there. If you have an object that is a continuous object, then you need to use calculus, and instead of the summation, then we need to integrate, and the integration actually looks more like we're going to do this for the 221 people, but we want to integrate r squared with respect to m, and that would give us the moment of inertia of a quantity. But again, that's calculus. That's only for physics 221. So if you haven't done any calculus, and if you're not in 221, you don't need to worry about it. If you are in 221, I'll do a couple of these for you at the end of all this, and you can see exactly how it works out. It's not hard. Just got to be a little tricky, a little clever in the way that you pick your axis and your variables. Since we don't know calculus, since we don't want to integrate all those things, what we can do is go look them up on a table. This is the table that you have in your book that's on page 330 or 332. One of these is the PDF number and one is the page number, but it's right there somewhere. You'll find this table in your textbook, and just about every textbook has some version of this. If I take a stick right here and I rotate it about one end of the stick, I can look up the moment of inertia. If I take the same stick that has mass m and length L, but I rotate it through the center of the stick instead of the end of the stick, that changes how far the mass is from my axis of rotation. That changes the moment of inertia, so I'll get a different value for the moment of inertia. And my responsibility is to say, well, my shape looks like a stick that's spun about one end or a stick that's spun about the center. And then I come to the table and I look up whatever the moment of inertia is. I'd have to know the mass of the stick and the length of the stick, and I could multiply that thing out. I realize this is going to be really small to see for you, but it's in your book. Go look it up. These are already done for you. Somebody has already done the calculus, so you don't have to. Here's another one. If I had a solid sphere, if I had a cannonball, that would rotate one way. If I had a thin spherical shell, a basketball, where all of the mass is on the outside of the surface, that changes where the mass is distributed, which means it's going to be either easier or harder to rotate that thing, and therefore I would have a different moment of inertia. This has all been done with calculus, but there's the value. If it's a solid sphere, I get 2/5 mr squared. If it's a hollow sphere, then I get 2/3 mr squared. If you convert those fractions to decimals, this would be 0.4 mr squared. This one would be 0.66 mr squared. This guy is harder to rotate than that guy. Over here, the stick, ml squared over 3, that's bigger than ml squared divided by 12. So this guy is harder to rotate than that guy. And that's all that table does. You need to look at your problem and say, what shape is my problem? Is it a hoop? Is it a disc? Is it a stick? Is it a sphere? And then pick the right moment of inertia. Put your numbers in for mass and length or mass and radius and calculate the moment of inertia, and then use that in the calculations. Right here, for example, 2 slides back, we worked this thing out and we said Newton's second law for linearly moving objects looks like this, but if it's a rotating object, it looks like this. The torque is equal to I, the moment of inertia, times alpha, the angular acceleration. So as soon as I know what the shape is, I go look it up on the table, put in the mass and the length, or the mass and the radius, and calculate I, and then I put it right there, and it does the same thing that mass used to do in Newton's second equation. Okay? Let's say that I have a baseball bat, and I'm going to spin this baseball bat about this point right here. So this is my axis of rotation, and I'm just going to make up some numbers here. The bat has a mass of 4 kilograms. That's probably kind of heavy, I don't know, and a length of what sounds good, 0.8 meters maybe, something like that. So the first thing that we probably want to do in this is to calculate the moment of inertia. In order to do that, I have to go look up the formula. So going back to that table, I would come here and say, well, I'm looking for something that looks like a baseball bat. And you can see that this does not look like a baseball bat. This kind of looks like a baseball bat, but notice how the axis is moving through the center of that. That would be like rotating a baseball bat, not spinning it about the end. This is the one that we need. There's the axis of rotation. There's the baseball bat coming off. ml squared over 3 is the formula that we need. So now that we know which formula to use, we come over here and we write down that I equals ml squared over 3. Okay, we have those numbers. The mass was 4 kilograms. The length is 0.8 meters. That has to be squared. We divide by 3. And I'm going to cheat here and use my calculator. When I do 4 times 0.8 squared divided by 3, I get a number, 0.853. Let's see here. There we go. 0.853 is the value for the moment of inertia of that object. Now, I would like to know the units, and I see that I have kilograms right there, and I have meters, which got squared right there. So that is the moment of inertia of that baseball bat. If it had more mass, it would be harder to spin, and I'd have a bigger number. If it were longer, it would be harder to spin, and I'd have a bigger number. But that's the number for how hard it is to spin. Let's say now that I apply a force out here on the end of this thing. Let's say that the force is equal to 15 newtons right there. And I'd like to know how fast that speeds up its rotation. When I push on it, I expect to see it speed up. In fact, we know that Newton's formula here, torque equals I alpha is what we're looking for. I'd like to find alpha. Okay, torque was force times distance equals I alpha. We just found I, so we can divide by that. And the angular acceleration, the rate of change of the angular velocity there, is going to be equal to Fr over I. The F was 15 newtons. The R, the distance here, let's say we're pushing out at the very end of it, so R is also equal to 0.8, but that could be any other number. They would give you that. And then I need to divide by this I right here, 0.853 kilogram meters squared, and that's going to be equal to alpha. So let me get my calculator back out here. 15 times 0.8 divided by that moment of inertia we just calculated would be 14.1. And it would be interesting to know what the units are here. On top I have newtons and meters. Down here I have kilogram meter per second squared. Let's remind ourselves that a newton is a kilogram meter per second squared. There's the second meter, and here's kilogram meter squared. So what I think I would do here is to cancel these kilograms with those ones. Here's a meter times a meter would be a meter squared on top, which will cancel the meters squared on the bottom. And what I end up with is 14.1 something over second squared. This is one of those times when the radian is just going to pop in, pop out. We saw that in chapter 6. So this is radians per second squared. We're looking for an angular acceleration. Right there's our angle. There's how fast it's speeding up. And 14.1 is the number that we need there. Let's do rotational kinetic energy. The nice thing about chapter 10 is that it takes everything that we've done all semester, and it lets us revisit that and see it one more time, and B, it makes a whole new physics for us. This is a formula that we've seen before. Back in chapter 7, the kinetic energy of an object was equal to 1/2 the mass times the velocity squared. Well, if we remind ourselves that velocity is r omega, and I pick up r omega and put it in right here, when I square that, I would get mass radius squared omega squared, the 1/2 still out front, and I take this mr squared right here, and that turns into I. So this thing, there's my 1/2, mr squared is the I, there's omega squared. Now I have a new formula, this thing, that tells me how much this would be the kinetic energy of a rotating object. And it works exactly like the kinetic energy of a linearly moving object, except this one's rotating. It would certainly take energy to get an object rotating. It would certainly take energy to stop it, and if it hit something, it would cause a transfer of energy there. So that's how to derive the rotational kinetic energy. Here is the work energy theorem, and I don't want to belabor this, but in chapter 7 we talked about the work energy theorem right there. Another way to write delta KE was 1/2 mv squared minus 1/2 mv naught squared. Right here I have a common factor of m, so we've pulled that out front. Now we've made our substitution where v equals r omega, so I put those in there, and you can see that the r squared is common in both terms, so I pull that out. There's an mr squared, which is an I. Here's my omega squared minus omega naught squared. There is the work energy theorem written for a rotating object. And so once again, the old physics becomes something new. When I take momentum, back in chapter 8, we had the momentum was equal to mass times velocity. Now I've got a quantity called angular momentum. L is the symbol for that. It's equal to I omega. Now I've been doing these derivations, but I think you can see the pattern here that if we just take x and we replace it with theta, if we take v and replace it with omega, and a replace it with alpha, we end up with all those kinematics formulas. Instead of F, we want to think about torque, force at a distance. Instead of mass, we need to use I, the moment of inertia. And so see how we've done this. Right here's mass, replace it with angular with the moment of inertia. Here is the linear velocity, replace that, and like we said right here, with angular velocity. And then my angular momentum, my regular momentum here becomes that angular momentum there. The picture of the skater is kind of traditional at this point to talk about. Here's the skater, and she's turning at some speed omega. The way her mass is distributed determines her moment of inertia. So we could calculate the angular momentum would be equal to her moment of inertia times her angular velocity. If she pulls her arms in, that changes the distribution of her mass, that changes the moment of inertia, and the angular momentum has to change as well. The angular momentum doesn't change, but the angular velocity right there will change. The way to do that is exactly like what we did with regular momentum. We did conservation of momentum. The momentum before was equal to the momentum afterwards, and we had this big formula. Now we want to conserve angular momentum. So the angular momentum before she pulls her arms in is equal to the angular momentum after she pulls her arms in. If you had two objects, you could do all this like we did up here. More often than not, it's one object, a skater or something, a merry-go-round, and so the angular momentum of the object, of the single object before, is equal to the angular momentum afterwards. I left off a little tick mark here, so let me put that in. There should be a little tick mark right there. Just like we did in momentum, the tick mark indicates the after quantity. So the moment of inertia after she pulls in her arms times the angular velocity after she pulls in her arms. Like that. Let's do one of these real quick. We'll just make up some numbers. Here is the skater. She's got her arms out and she's spinning here. And just to make this easy, let's say that I is equal to 40 kilogram meter squared. Don't know if that's a good number or not. She is spinning at 2 radians per second. Okay, so that's the before picture. That's what's happening before. Then she decides to pull her arms in, and so now she's like this. You can see that her mass is closer in. That means that it's easier to spin. When it's closer to the axis of rotation, it's easier to spin. My moment of inertia is going to go down here, and so I'll call this I prime, but that's going to go down. And I'm going to just make up a number here. Let's say that it goes down to 20 kilogram meter squared. Okay. I'd like to know what her final angular velocity is. So all I have to do here is to make sure that we conserve angular momentum. So L has to equal L prime. L was I omega, which would be equal to I prime omega prime. Just using before on the left and after on the right. I've got 3 of these numbers. We just set it up like a proportion. Looks like this. I'd have 40 kilogram meter squared, my initial moment of inertia times my initial angular velocity, and then divide by the final moment of inertia there. And this would be 40 times 2 would be 80 divided by 2. Her speed goes up to 4 radians per second. It has to in order to conserve angular momentum. When she puts her arms back out, she'll slow back down again in order to conserve angular momentum. So this little table right here shows all of the formulas, and I really like this table because this is pretty much everything that we've done all semester long, and then we convert it over to this table right here. This is for the linear variables and the linear quantities. This is all rotational over here. We got a whole new physics for free. We just converted the variable names over. Here's that list again. X turns into theta. V turns into omega. A turns into alpha. M turns into I. F turns into torque. Is that everything? Oh, and P becomes angular momentum, L, like that. Just by simply replacing the variables, we get a whole new physics. And I think that's kind of neat. You may want to put something like that on your card. You know, if you root through this thing, right there's chapter 2 and 3. Right here, this is chapter 4. I'm sorry, chapter 7. This was chapter 4 and 5. Down here's chapter 8. Right, so see how there's everything right there that we have, and the perfect parallel to it over on the other side. So that's kind of nifty. Before we move on, I want to do one more thing here. We talked about this ice skater, and you know, if you were to think about her shape and what we need to use for the moment of inertia, what we can do with that table is we can cut the ice skater into parts. I don't know that she'll like that very much, but We could deconstruct the ice skater, and it would look something like that, right? Maybe her legs are part of her torso there, or if you want to really get fancy, then there's a way that we can do that as well, called the parallel axis theorem. But these shapes are on the table, right? When we go back to that table, we recognize her head looks quite a bit like a sphere, and the moment of inertia of a sphere was 2/5 mr squared. Now, of course, that's the mass of her head times the radius of her head. Okay? So it's not the mass of the whole skater, just her head, just the sphere part. Her torso here is a nice cylinder. The axis of rotation is right down through the middle of that thing. Okay? But we have the moment of inertia for a cylinder. It's 1/2 mr squared. And again, that'd be the mass of the torso and the radius of the torso. Not her head, not her whole body, anything like that. All right? Then I've got these two arms that stick off. The first arm has a length of something and a mass of something. So for her arm, then I could write out that the moment of inertia of her arm is equal to 1/3 ml squared, and of course that's her arm and her arm right here. Okay, and I'd have the same thing over here. And so what we did was we took a shape that is not on our table, but now I want the total moment of inertia of the skater. And I can say, well, it's the moment of inertia of her head plus the moment of inertia of her torso plus 2 times the moment of inertia of her arms. And I could put all those pieces together. And as long as I keep all the parts in the right place, this should work out fine. Okay, and we could get all those numbers. The skater might not like it because we're going to have to cut off her arms, cut off her head, and get the individual masses there. But maybe we could come up with another way to get numbers for that. For those of you in 221, let's consider her leg just a moment here. Her leg looks like that, but the axis of rotation is over here, and her leg is spinning around the axis of rotation. We have a formula that gives us the moment of inertia of that leg about this axis. We would like to find it about a new axis that runs parallel to that. And so there is a thing called the parallel axis theorem that allows us to take a moment of inertia that we know and to slide the axis over. It's very easy to use. The moment of inertia about this new axis, and they usually call this the z-axis and this the cm, the center of mass, is equal to the old moment of inertia plus md squared. So the m would be the mass of her leg. The d here is the distance that we had to move that axis to make it work, right there. Okay, so d is how far we shifted the axis from the old axis, the center of running through the center of mass, to the center of her body, and that step off right there would be d. We need the mass of her leg, and then right here we could look this part up on the table. For a cylinder, it was 1/2 mr squared, and so that would be the axis of about that z thing for her leg. And if you wanted to, you could get this number and add it in there, and actually you need to add it twice. I'll just call that IZ there, for her legs, unless you want to just include it as part of her torso. But the parallel axis theorem is a pretty good way to do that. There's actually also a perpendicular axis theorem. We can turn it perpendicular to itself too, but we won't worry about that one today. Now, this is for 221 people, so if the 201 people want to go away at this point, that's fine. This is how they made that table. This is how they got those values for the moment of inertia for continuous objects. And the first one I'd like to consider down here is a long skinny stick, a rod. Okay, so this is a thin rod. We're going to rotate it about one end of the rod. You can see the axis of rotation right there. And just like we do in all calculus, what we do is we take a little bitty slice of the object right there, some thickness, and we're going to call the thickness dr here, and we're going to let that dr move from one end down to the other, and we're going to add each little bit of that. We're going to integrate to get the total. Integration adds the area under a curve. It sums up the total effect of something. So right here, if I get the moment of inertia of this little piece and add to it the moment of inertia of the next little piece and the next little piece and all the way down, then I'll have my total moment of inertia for that long skinny rod that's rotated about one end. So there's a couple things we have to set up, a couple definitions. The first one here is the density of the object. So we're using the Greek letter rho to be that. The density is rho. And to get the density, all I have to do is take the total mass, divide by the total length. We're assuming that this is a uniformly distributed rod, that it's the same mass per inch, mass per meter, whatever, all the way down. Okay, so I've taken the mass and I've cut it up, divided it by however long it is. Next thing I need to do, that was step number 1, and we've done that. Step number 2 is always to find dm. So the way that we do that is to take the density of the material and multiply by the length of the material. Remember, we were talking about this little slice right there. And when I think about that little slice, I need to know the mass of that little slice, and then I'm going to do something with the distance from the axis of rotation and find out the moment of inertia of that little slice, and then I'll add the moment of inertia of each other little slice. The calculus does that for me, and I don't have to worry about it too much. Okay, but the density times the thickness of that slice gives me the mass of that little differential slice of the rod. The third step, now that we've done step 2, is to set this thing up, and that's not hard. It's always the same formula. This is what you always want to do on these things. The moment of inertia is always equal to the integral of the radius squared with respect to mass. Integral r squared dm. Since we have dm, here's the way I set that up. I take dm right here equal to rho dr and just substitute it in. The rho is a constant, right? We said that the density was constant over the whole thing. So pull that out front. We've put it out front here. I need to integrate r squared with respect to r. Of course, that would give me r cubed over 3. And my limits of integration there would be to go from one end of the rod, r, the distance from the axis of rotation to this end is 0, and go all the way to the other end where r, the distance from the axis of rotation to the end, to my little slice is L. And so those are my limits of integration. I put in the L for r, it goes right there. When I subtract and put in 0, that's just minus rho 0 cubed divided by 3, and the 0 kills it all there, so we don't worry about it. All right, and then we're going to substitute back in this rho was equal to m over L. That L on the bottom cancels one of the L's on top, and I end up with ml squared over 3. That's how they got that formula that's on the table. I equals ml squared over 3 for a thin rod about one end. Okay, So you could do that. It's already done. It's on the table, but that's how they did it. Let's look at another one here. If I take the same rod, the same thin rod, it's got the same mass, same length, but this time we want to rotate it about the center. You know, maybe this is a helicopter blade. Instead of a fishing pole where I'm holding on to one end, maybe it's a baton, right, that a cheerleader has or something. She's spinning it about the middle. Okay, so I use the same density. I'm still taking the total mass of the rod, cutting it up by the total length to get a mass per length, the total density. I need to find dm in step 2. The dm, again, is going to be equal to the density times the thickness of that slice, of any little differential slice. So I've got that. This time my limits of integration are going to go from this end of the rod to there. The entire length of the rod is L, so I've got half the length of the rod on the left and half of it on the right. R is going to go from negative L over 2 to 0 all the way to L over 2. I'm measuring from the middle, and I'd have to go half of the length this way and half of the length that way. Here's my setup right there, and again here. We know that dm is equal to rho dr, so I put that in. The rho, again, is a constant, comes out front, and I integrate r squared with respect to r. I'd get r cubed over 3, and there are my limits. I take the upper limit and I put it in, and then I subtract what happens when I put the lower limit in right there. Cubing L would give me L cubed. Cubing 2 would give me an 8. That'll be on the bottom. I've also got a 3 on the bottom, so 8 times 3 would be 24. Subtracting the lower limit. The rho's out front. I've got an L, which gets cubed. That's actually a negative L, which gets cubed. So negative L times negative L times negative L would be negative L cubed. On the bottom, I've got a 2, which gets cubed. That's an 8. Again, it's on the bottom. The 3 is on the bottom. 8 times 3 would be 24. And then this negative sign and that negative sign go together to make a positive right there. And factoring that L out front, I've got L cubed plus L cubed would be 2L cubed all over 24. The 2 goes into 24 12 times. So there's my thing. We substitute back in for this density up here, m over L, and that L cancels one of those, and I end up with that formula. The moment of inertia is equal to ml squared over 12. This is the same rod, but now I'm rotating about the center. Because my mass is closer in, it doesn't go all the way out to L, it only goes out to L over 2. Because it's closer in, that makes it easier to spin, and I get a lower moment of inertia. Okay, one more for you here, just to show you how much fun these can be. This one is a disc about the center. We saw on the table that the moment of inertia was 1/2 mr squared. This is why. This is how. We've got our disc right here, and we can cut that disc up any way that we want to, but if we cut it up into little concentric rings like you see here, then we have preserved the symmetry of the problem. Every point on that outer ring right there is the same distance away from the axis of rotation, and that makes it easier to integrate. Makes it easier to set up and to integrate. Step 1, we need to define the density. This time, because it's a area, it's mass per area instead of mass per length, we use the Greek letter sigma. That's the lower case sigma. That's kind of a picky point, but we used rho when it was a linear density, and here it's an area density, so we use sigma. But it's simply the mass divided by the area that is spread out over. You know that this is a circle, so I've got the mass, and the area of that circle would be pi r squared. So you could also write it that way if you want to. Step 2 was to find the mass of one of these little slices. So I'm thinking about this little ring, this little donut that I've cut out of the dough here, right? And I need to know how much mass that ring has and how far away it is from my axis of rotation. And then I can get the moment of inertia of that little ring and add it to all the other little rings like that. Okay, so here we go. The mass of that little differential slice is equal to the density times the amount of area that I've got there. The area of that little piece, this is a circle, and the distance around that circle would be 2 pi r. The thickness of that circle is dr. So if I multiply 2 pi r times dr, then I would have the area of that little piece right there. And when I multiply the area times the density, sigma, then I would get the mass of that little green shaded ring. So that's the part that I need to have. I have to plug that in for dm, so it comes in right here. I always want to integrate r squared with respect to m. So there's r squared. Here's my dm that I just put in, sigma 2 pi r dr. Pull all the constants out. Sigma is a constant, so it came out front. Pi is a constant, it comes out front. That leaves me an r squared here and an r there, making r cubed, which I want to integrate with respect to r. And here's all those constants, 2, sigma, pi. The integral of r cubed would be r cubed over 4. And then we've done a little thing where the 2 goes into 4 2 times. So we've simplified that right here as much as we possibly can. Our limits of integration are here. So I want to put in that upper one right there, and then subtract what happens when I put in the lower one right there. And you can see that on the next step. Here's the upper limit of integration. The lower limit of integration is 0. 0 to the 4th times all those constants is still 0. So I don't have to worry about that part. Now we can put in sigma. Sigma is equal to ma, or m over a, or as we said, m over pi r squared. So we put this into right there for sigma, and I would have m over pi r squared times pi r4 over 2. This pi on the bottom and this pi on the top cancel. This r squared on the bottom cancels 2 of those, and I end up with mr squared over 2, or as we like to write it, I of a disk is equal to 1/2 mr squared. We did not say anything about the thickness of this disk because the thickness doesn't really matter. If this were a really thick disk, like you see here, then I am still the same distance r away from the center, or from the axis of rotation. All I care about is how far from the axis of rotation is it. So this is the moment of inertia for, come on now, for a disk or a ring. It's the same thing. The thickness of it doesn't matter, just the radius and the mass. And that's all we have. All right, so that's chapter 10. Thank you for listening. We'll be back together for any questions that you have, and have a fantastic day.